Hello everyone, welcome to ECE331. Let's get straight into it. So I'm going to give a brief overview of the equipment that you're going to use for this lab and for future labs. And then I'm going to actually pull out these modules separately so you can see what's behind the hood, so that you can get a better grasp of what's happening here. What are these things that we're using? Okay, and I'll just say that this whole thing is called the Lab Volt Electromechanical Training System. Okay, and I abbreviate this to LV-EMTS in the lab manuals. Okay, so remember that Lab Volt Electromechanical Training System abbreviated to LV-EMTS. All right. Okay, so we're starting off with the power supply module. So what you need to know about this for now is there are two different AC power supplies, you could say, and each of those power supplies is a three-phase Y-configured power supply. Okay, and that should kind of make sense. You have three live terminals and then neutral one. There's also ground there, but Y-configured power sources have three actives and a neutral at least. If this was delta, the neutral line wouldn't be there. And you can also see this is the classic 12208 Y. It's not written there Y, but that phrase 12208 Y is very common in the industry, and you should know that really well. Okay, but anyways, for this lab we're using this power supply, these three, because this is the variable power supply. You can see here it says 0 to 120, and we vary that with this knob over here. This power supply is fixed at 120 208. And by the way, hopefully you know why we have two numbers there, 120 and 208. If you don't, then ask me, because you really should know. Okay, but anyways, I'm not going to say it in the video here. There are also DC power supplies, but that is not going to be used for this lab. It's going to be used later on when we work with the generators and motors. And so, yep, okay, there's that. Then we have the voltage control knob for these variable sources. This is the variable AC source. We also have the variable DC source. Both of these are changed with the same knob. And for this knob over here, the numbers on it are not voltages, they are percentages of the maximum. Okay, so 0% would be 0 volts, 100% would be 120 volts line to neutral. Okay, so just be careful of that. The way that you can kind of see that live in action, like what the actual voltage is with this analog meter over here. This analog meter is going to measure whatever this rotary encoder is set at. Right now it's set at 4N, so as in it's going to be measuring the voltage between these two terminals over here, 4 and N. And so as you vary this, don't look at the percentage necessarily, look at the voltage displayed here, and that should give you at least a rough idea of where the actual voltage is. Of course, in your labs, you're also going to be using the data acquisition interface, which is basically going to act as your multimeter, oscilloscope, and what have you, so that you can see a little more in detail what the voltage is actually at. Okay, but there's that. And then, you have your big power switch, which is for these over here. Okay, and as a quick safety tip, before you power your circuit, of course, before you power your circuit, make sure everything is wired up already and your circuit is set and you have the terminals already connected in, and then you can power on your circuit. When you power it on, the voltage control knob should be at 0 so that you don't accidentally shock your circuit with a sudden spike of voltage. And once you turn this on, and this is at 0 before you turn it on, you slowly raise the voltage to whatever it needs to be. This is a little tough to turn, by the way, so just don't try and go super duper slow, because it does take a little bit of effort to turn this. But there's that. You'll also be able to tell whether all your three lines, your three actives, are working if these LEDs are on. These are what these LEDs are for. They indicate whether these voltages are working or not, your lines. And then finally, you have this 24 volt AC power supply. This is to supply other modules that need it. For example, the data acquisition interface module, it needs 24 volts. That's what this input is over here. The dynamometer module also requires that. And so you would supply it over here as well for that. Okay, so that's what this is for. It's not operated with this switch. It has its own switch over there. So for example, you can have your circuit off but the data acquisition module is still on measuring voltages and so on. And you'll find that that is handy because the interface will give you an error message if the data acquisition interface is not actively being powered. All right, so there is that. So this is the power supply module taken out. And you can see here, this is what we were seeing, the front panel before. Here's what's behind the hood. You see these three things right away. They're directly apparent. I'll come to that in a second, but I'll start by saying that this module gets its power from this receptacle over here, which connects to the three-phase power in the wall. If you see something like this, you know, something like this. This is a three-phase power a receptacle in the plug in the wall that you connect something like this to. This is called an L2120 connector, okay, a NEMA L2120. This is again in my notes on the power supply module, you should know this, but this is a 20 amp rated connector with 4 I should say. No, there should be 5. In any case, okay, we have our 3 phases plus ground and neutral, okay, and that's what we get from that. So that is connected to the power supply module. On the back over here, you can see this is the receiving end of the connection, and our 3 phases go through. And then, okay, we have our 3 auto transformers over here. This is what you'll see. So look, this was the voltage control knob to control the voltage. If I turn this, you will see that this mechanism over here is kind of, you know, probing a different point in the wires. And when you guys learn about auto transformers, hopefully this will make a lot more sense. But anyways, I'm basically changing how many windings I am at on the secondary of the auto transformer. Okay, so all the way, I'm getting all the windings through, in which case this would be a 1-to-1 transformer. And then, you know, as I decrease the amount of windings I have on the secondary, then it becomes a step-down transformer, auto transformer, okay? So we just have 3 of them for the 3 phases, and that's how we get our variable supply. Over here, we get our fixed supply, which is just directly connected to the receptacle over here, and we get our DC power supplies because there's a board on the bottom of this, which I'm not going to show, which rectifies that AC, does some power electronics on it, and then gives us our desired output over here. Okay, and then you see the other stuff for the analog module, for example, but I'm not going to go over that. All right, but yeah, that's what's under the hood, at least an overview. I'll just get another view here so people can see, maybe ponder a little bit on what's behind. All right. Okay, sorry guys, my girlfriend scared me there. Extra 2 bonus points if you actually mention this in your lab report, because I'll know then that you watched the videos. But anyways, if you connect a capacitor and an inductor in parallel with the same, you know, magnitude of impedance, they would resonate and they'd cancel each other out. The admittance overall would be 0, so you'd have an open circuit. If you connected them in series, that would result in a short. Okay, but anyways, just be careful of this. This is showing the magnitude of the impedance, but in reactance, you would have that as negative, as in it's towards the negative axis of the complex plane, okay, for the impedances. All right. Okay, guys, these are the load modules pulled out, so you can see what's behind the front panel. You can clearly see this is the resistive module, the inductive module, and the capacitive module. And then, okay, we'll start with the resistive one. I just want to say something that is often neglected. What are these resistors called, or what are these particular inductors called? Okay, that's what I want to go over. These resistors are called wire wound resistors, and they're power wire wound resistors, as in to achieve their resistance. Instead of having, for example, a material between 2 leads, they have just a wire that's wound around a usually ceramic core, or something that doesn't have much dielectric or a magnetic constant. But anyways, they have a wire wound around the core, and then it's wound in a specific way to ensure that the inductance caused by that winding would be too high. Okay, but anyways, these are wire wound power resistors, and it's because of their winding they get the resistance, and also depending on the gauge of the wire you use, they also may achieve higher power rating as well than what you would if you had just a small material between 2 leads. Okay, another thing to note is, which of these do you think is the higher resistance? Is it, you know, these larger ones or the smaller one? And it's actually the smaller ones that are higher resistance than these larger ones. So that 1200 ohms is these, and those are the 300 ohm ones, okay? And maybe ponder on that a little bit, thinking about how cross-sectional area might affect resistance. Okay, so those are our resistor modules, or resistors in the resistor module. This is the inductive bank, and we have over here what are called core or magnetic core inductors. Okay, and it's very similar to what a transformer might look like, by the way. And one way you can tell the difference is, and you'll see later in the lab, in another lab, we'll see how a transformer looks. But anyways, these can be differentiated from what a transformer might be. If you see the number of leads out here, they're just two wires. It's hard to see, but there are only two leads, two terminals, and that's clearly an inductor. A transformer will have at least four, if not more than that. Okay, and these are called core. Okay, so core inductors or magnetic core inductors because they're a winding around a core, much like a solenoid, and that core is usually magnetic. Something like iron, for example, would make up the core. And actually, because these are wound around a core that's magnetic, these inductors will face the same type of issues that you will find with transformers. When you learn about transformers, things like hysteresis and core losses, like eddy currents, and what have you, those will also appear over here. But anyways, these are the inductors. One of the questions I ask, a big bonus question I ask, is what do you think the core's magnetic constant, okay, will be, or relative permeability, let's say, will be, and just take a guess at what that might be. For example, these are the 3.2 Henry inductors, based on the cross-sectional area and what you think the length of the solenoid is, and what have you. Just make a back of the napkin type calculation as to what the relative permeability of the core would need to be in order to achieve the inductance that you see here. Okay, so that's those are the inductors. Finally, we have here our capacitors. These are called power film capacitors, okay, because they are rated for higher power. They're not like the aluminum electrolytic capacitors that we see in electronics or the ceramic capacitors. These are film capacitors, first of all, and they are power film capacitors, which means the dielectric material between the two capacitor plates used usually will have a much higher a dielectric breakdown voltage, and also has a decent enough dielectric constant to give us high enough capacitance values. Okay, and in fact these particular ones, I think they have oil as their dielectric. Okay, but anyways, that's the capacitor bank. So I just want you to note the materials used to make these power loads. All right, and finally guys, we have the data acquisition interface module. Okay, it's just this rectangular portion over here, not including the synchronizing module. And it's very straightforward. These are the voltages if we want to measure voltages, and you connect these in parallel with whatever voltage you're trying to measure. And these are the currents. You connect these in series with whatever current you're trying to measure. Okay, and that's pretty much it for that. You also need to provide power to this data acquisition module. It doesn't have like power coming from the back. So it has this 24 volt needed power supply, which comes from that 24 volt we saw earlier, the power supply module. All these other things, the analog inputs, outputs, and stuff, this we'll see later on when we're working with the dynamometers, data module, let's say. All right. Okay. So that's data acquisition interface. Sorry, I should also say this computer I/O USB port. That's what you would connect to your computer in order to actually interact with this and get this data and display it using the data acquisition software that comes with this whole system. All right.